Emmy here again, and welcome to another episode of COBB. Now, as we continue our journey through the components that make up a modern turbocharged engine, we've come to our next set of parts, the boost control system. Since this series is aimed towards educating the newcomer, this episode we're going to focus more on how the system works overall. The core function of boost control is to manage boost, so many enthusiasts will find that they don't need to upgrade these components until later down the line, when the stock parts no longer meet their needs. So keep this in mind as we go along. Okay, first things first, boost. Maybe you've heard it. Maybe you've heard people talking about it or even bragging about it. It's one of the most used and least understood terms among many car enthusiasts. So what is boost and why do I even care about it? The topic is often danced around, so today we're going to dig a little deeper. Now get ready because I'm about to throw a lot of information at you. You've probably heard the weatherman talk about barometric pressure. That's the pressure of the air around us. When we talk about air pressure going in an engine, we often compare that pressure to the barometric pressure. Anytime the pressure going into the engine is higher than barometric, the difference in the two pressures is your boost level. So as an example, if the pressure going into the engine measures 30.6 psi absolute, and the barometric pressure right now is 14.6 psi absolute, the difference of the two is 16 psi of boost. They call it boost because pushing more air into an engine than it can naturally inhale allows for a boost in performance. So the more air you can cram into a cylinder, the more fuel you can add to it, which increases combustion energy. The more energy equals more power. Now this explains why turbocharged engines are referred to as forced induction, and those without turbos are called naturally aspirated or naturally breathing. Keep in mind that this is a good thing, only being good in moderation. If you run too much boost, you can damage your engine. There's also an operating range for your turbo, and if you exceed its limits, you could cause turbo failure. While less dramatic and before that happens, there's a point where increasing boost offers little to no power gains and only increases wear on your components. This is based on a number of factors, such as airflow restrictions of the housing itself and wheel efficiency. To learn more about turbo efficiency, you can visit the extra credit below. While we're on this subject, I want to touch on a misconception which we hear a lot about from our customers and within the community, which is an over-concern about the amount of boost pressure. There's a lot more to making power efficiently than hitting 22.3 pounds of boost. The assumption is that the higher the boost number equals good, and that's not necessarily the case. What's important is creating the appropriate amount of boost for your setup, because every setup is completely different. Some engines are designed to operate at a higher boost pressure, while others run more efficiently with less. So just because you can make more boost doesn't necessarily mean you should use it. This is a great example of why having a good understanding of your engine, its design, and capabilities is extremely important. Another thing to consider is the size of the turbo. The bigger the turbo, the more air you can push in comparison to its smaller counterpart. And we've learned that the more air you can force into an engine, the more power you can make. So, since the larger turbo can push more air, it can create more power at a lower boost pressure. So the larger turbo may only need to run at 6 psi, while the smaller turbo might have to run at 12 psi to create the same amount of power. Now, the size of the turbo that you go with is determined strictly upon your setup and your performance needs. Now that we know what boost is, let's talk about how it's created. This is done one of two ways, either with a turbo or a supercharger. For this series, we're going to stick to turbo setups because that's what COBB supports. For those of you that are interested in learning about superchargers, you can click on the link in the extra credit below. For this demonstration, we'll be using components for a stock location turbo on a Subaru WRX STI, so your components and setup might look different, but overall, the concept is the same. The components we're going to talk about today are the turbo inlet hose, the turbo itself, the wastegate, which in this case is on the turbo, an electronic boost control solenoid or boost controller, and various hoses and clamps. The turbo inlet hose, as the name suggests, is the inlet to the turbo. Now, this is one part that we do recommend upgrading, and here's why. Here, I have a stock turbo inlet hose. This part, plastic. This part is rubber. It gets clamped to the turbo. Over time, this rubber part becomes brittle and fails, like this right here. When that happens, air can either enter or exit the intake system after it's already been measured by the MAF sensor. Remember that the MAF sensor sits just past the intake filter and is measuring how much air is coming in. The ECU takes that MAF reading along with others and calculates the amount of fuel needed to achieve the appropriate air-fuel mixture. Now the ECU is assuming that all the air passing through the MAF sensor is going into the engine. So if you have some air escaping or sneaking into the intake, then it's going to be injecting too much or not enough fuel, and this can make your engine run poorly. An upgraded turbo inlet generally is made of metal or silicone, like this one right here. That's for a couple of reasons. First, it's more durable, so you're going to get more life out of it. Second, it allows for better airflow because the internal walls are smooth. Unlike this stock turbo inlet that has these accordion ribs right here, which is going to cause turbulence. You'll notice that the inlet has 4 ports on the side. These 2 are used for emissions control, which we won't be getting into in this series since it's a complicated system which shouldn't be modified on street-driven vehicles. Your bypass valve recirculates air to this port here. We'll get into the bypass valve in our next episode. And this last one will connect to the vent port on your boost controller. Air is diverted here when we want to increase boost. Next up is the turbo itself. The turbo is made of 2 separate halves, connected in the middle by a center housing and rotating assembly. One side is referred to as the cold side, while the other is the hot side. Looking at this turbo that graciously donated its life to our cause, you see the 2 sides as well as the wheels, bearing housing, water and oil passages, and the shaft that connects the wheels together. So when one spins, the other does too. The cold side houses the compressor wheel, while the hot side houses the turbine wheel. You'll notice that both halves and the center section have various connection points. Starting on the cold side, this is where the turbo inlet connects, and this is where the intercooler piping will connect to. The small nipple here will connect to the boost controller hose. On the hot side, this is where the exhaust manifold or up pipe will connect to. In specific cases, like our Subaru motor, the up pipe is an intermediate pipe which joins the exhaust manifold to the turbo. The last connection point is where the down pipe will connect. In the center housing, we find our water ports and oil inlet and drain. And lastly, we have our internal wastegate, which is made up of an actuator, arm, and flapper. It's referred to as internal because it's built into the turbo itself. Moving on, we have our 3-port electronic boost control solenoid, or again, boost controller for short. Keep in mind that the factory Subaru boost controller has 2 ports, so the hose routing will be different, but the functionality will be the same. The boost controller is the one component that the ECU directly controls to increase or decrease boost by routing air either to or away from the wastegate actuator. On a 3-port unit, this port is where the air enters, and these 2 ports are where the air gets diverted to. A boost controller is essentially a valve with a small piston inside it that is either open or closed to route the air one way or another. To increase boost, the piston opens and routes the air through here. To decrease boost, the piston closes and routes air through here. This happens several times a second. The greater the percentage of the time the valve is open versus closed, the more boost the turbo can build. Now that we've seen the components, how does it all come together? Well, to explain this, we're going to separate it into 2 topics. First, the interaction between the air and the turbo. And second, how boost is actually managed. Keep in mind that although we're explaining these separately, everything we discuss happens simultaneously. We'll start here with the turbo inlet hose. We've already come past the air intake system and are now getting ready to enter the turbo. The turbo inlet hose not only serves as the inlet to the turbo, but also connects to the boost controller, keeping air at vents from leaving the system. Now we've reached the turbo, where boost is born. The air from our intake enters through the cold side of the turbo and meets the compressor wheel. As the wheel spins, it compresses the air and sends it on its way through the hot pipes and into the intercooler to get cooled. At the same time, compressed air is being routed from this nipple to the inlet port on the boost controller. We'll get back to this in a minute. Cooling is important because as the air is compressed into the turbo, it gets hotter. Hot air expands, taking up more space. Cold air contracts, allowing more air to fit into the engine. Very hot air can make combustion more volatile, which can lead to engine damage. The cooled air then travels up the cold pipes and into the intake manifold, where it will combine with fuel and go through the combustion process inside the cylinders. After the combustion process, the exhaust gases make their way out of the exhaust manifold under pressure and either enter the turbo directly, or, like in our Subaru motor, through an up pipe first and then the turbo. As the gases enter the turbo, they spin the turbine wheel and then make their way out through the downpipe. If the wastegate is open, some will bypass the wheel and flow straight into the downpipe. The amount of exhaust gases the wastegate bypasses away from the turbine wheel directly affects how fast the turbo spins. Since the turbine and compressor wheels are connected by a common shaft, they spin at the same speed. Now that we've gone through the air path, let's focus on how boost is managed, starting with the wastegate. This flapper here is normally closed due to a diaphragm and spring combo that's in the actuator. When pressure is applied to the actuator, it pushes against the diaphragm and spring, which in turn pushes this arm. If the air pressure applied to the actuator is higher than the pressure of the spring inside it, the flapper door is moved open to help us divert some of these gases away from the turbine wheel, thereby limiting its speed, and as a result, boost is reduced. When the flapper door is closed, the exhaust gases all route through the turbine wheel, providing maximum turbo output. Most stock turbos come equipped with an internal wastegate, but you may have heard somebody refer to an external wastegate. An external and an internal work the same. However, an external wastegate is generally found separate from the turbo. You might find this scenario in an upgraded turbo setup where you need to divert more exhaust gases than an internal setup allows. Now that we know how the wastegate affects boost, how do we control when it opens and closes? As I mentioned earlier, the boost controller is the actual component that the ECU controls to increase or decrease boost by routing air through one of these two hoses. The air comes into the boost controller from this nipple on the compressor side of the turbo. To increase boost, the ECU will open the piston and the air will divert from this port and enter the turbo inlet hose here, where it will be recycled back into the airflow. To reduce boost, the ECU will close this piston and divert air from this port to the wastegate. The wastegate flapper opens, the turbine wheel slows down, and boost is reduced. The ECU makes decisions to increase or decrease boost constantly, based on driving and atmospheric conditions, as well as readings from critical engine sensors like the MAP sensor. The MAP sensor, short for manifold absolute pressure, is located just after the butterfly valve in the throttle body and measures the pressure of the air in the intake manifold. As you accelerate and more air is compressed, the pressure of the air leaving the turbo increases. The tune that is flashed to your ECU will have a specific pressure reading that it tries to achieve based on current driving conditions. This is known as the boost target. When the MAP sensor reads pressure over the target, the ECU will then close the piston in the boost controller to route the air to the wastegate actuator, which will then open the flapper door to reduce boost. Once the pressure falls below the target, air is then rerouted back into the inlet hose to reduce wastegate flow and allow the turbine wheel to spin faster. Through proper tuning, not only can you control how much boost you make, but you can also control other characteristics too, like how quickly your turbo spools up, or how much boost you can sustain at a higher RPM. Thanks to the ECU, this switch isn't merely just on or off. It can cycle many times a second to help modulate boost. Okay, that was a ton of information, so let's quickly do a recap and see it all happen together. Air enters the intake and travels through the turbo inlet hose to the cold side of the turbo. As the turbo spins, the air gets compressed and then travels to the intercooler before making its way to the engine. After the combustion cycle, the exhaust gases exit the exhaust manifold and travel into the hot side of the turbo to spin the turbine wheel before making their way out of the exhaust. While this is happening, the boost controller's valve is opening and shutting, sending air to the inlet or wastegate to manage boost. If the boost controller routes air to the inlet, boost is increased. If it routes to the wastegate, boost is decreased. All of this happens over and over again as you're driving, and while you don't even notice what's going on inside your turbo, there's quite a bit of stress and heat building up. Turbos are designed to handle a certain amount of that heat and stress. As you accelerate and boost builds, the turbine and compressor wheels will continue to spin faster and faster. Turbo wheels are designed to spin at over 100,000 RPM, which is insane considering most engines live at under 10,000 RPM. All of this spinning is a result of over 1,000-degree exhaust gases passing through the turbine housing. Now the only problem is heat gets transferred to the center section and can damage the bearings inside. Which brings us to our last section, turbo cooling. Modern turbos have integrated oil and water lines to keep all moving parts running at a safe temperature. As your engine runs, it circulates oil into the turbo through here and out through here. Now, oil is not only used to lubricate the parts inside, but it's also used as a main source of cooling, as it absorbs heat that builds up in the bearings. Water is also used as a secondary source of cooling and enters and exits here. A key benefit to water cooling actually comes after the engine is shut off, which stops the oil from circulating. Thanks to a phenomenon called thermal siphoning, water won't stop circulating right away. You can actually hear it moving in the engine until it cools off. Because the water will continue to flow, it goes through the turbo and absorbs more heat. If you want to learn more about thermal siphoning, you can check out our extra credit link below. That's it! See, it wasn't so bad, was it? As usual, anytime we're making changes to our hard parts, we need to make sure that we have the right calibration flash to the ECU. And if you're modifying any of the parts that we touched on in this video, you're most likely going to have to flash a new tune. If you're still unsure, you can contact us or your local COBB Pro tuner, and we can answer any of your questions and set your mind at ease. Lastly, when doing this type of part install, you will generally use these kinds of tools: ratchets, sockets, and extensions, screwdrivers, picks, needle nose pliers, dikes for cutting, and silicone spray. That's going to do it for this episode. In our next video, we're going to follow the air as it makes its way to the intercooler to chill out before combustion. Thanks for joining us, and be sure to subscribe to our YouTube channel. I'm Emmy, your host for COBBU. Remember, check out cobbtuning.com for all your parts and tuning needs. Do you like the storage solutions featured in our studio? Then visit SonicToolsUSA.com to get more detailed product information.